All right. The last speaker of this session is Ian Moult, who's going to tell us about energy correlators of the collider frontier.
Okay, so thank you very much to the organizers for this nice conference and for the opportunity to speak. So as you can probably tell from the title, this talk is going to be thematically quite different than the rest of the talks in this session. And I'm going to be talking about a particular class of observables, which are called energy correlators, which are used to characterize the energy flow in collider experiments. And so because it's quite different, the goal of this talk will be to give kind of a broad overview of some of the work in this area that's been going on recently. In particular, trying to highlight the connections between theory and experiment, and to kind of make you aware of some of the experimental measurements which have been made in the last year or so, which I think are starting to become closer what is actually interesting to a theory audience. So when people typically think of collider physics, they often think of exclusive scattering processes or scattering amplitudes. And so these are objects that we understand quite well. So we now have quite a good understanding of their analytic structure. There's been a huge amount of progress, particularly in the last decade or so, in the perturbative structure of scattering amplitudes. And then more recently, there's been very nice work in the S-matrix bootstrap. And so from a practical perspective, what this allows people to do is to compute at very high energies in perturbation theory a huge wealth of very complicated scattering processes at the LHC, so for example involving many W and Z bosons. And then also more recently, using both effective field theory and bootstrap, people are starting to be able to compute low energy exclusive scattering for hadronic states. But if you go to colliders, it's kind of a very complementary regime, which is a kind of different type of collision where you have extremely high multiplicity. And so in QCD, this is realized because you have the energy much, much bigger than the kind of mass of the particles. And so instead of just having a couple particles coming out, you get these very impressive event displays. And so this is in proton-proton, and it's even kind of crazier in heavy ion collisions. And so in these cases, the kind of good observables are not scattering amplitudes, but rather kind of correlations in certain fluxes which are coming off to infinity. And so if you want to, for example, learn about certain properties of the quark gluon plasma, or if you want to learn about some kind of dynamics of the confinement transition, in particular going from quarks and gluons to hadrons in your detector, you kind of need to understand how to work with these classes of observables. And compared to their amplitude counterparts, they're very much less understood. And so these have an extremely long history, which is kind of intertwined with the history of QCD. And so I'm not going to obviously go into it too much, and in particular, just restrict it to 3 bullet points for the kind of 50-year history of these observables. And so right after the discovery of asymptotic freedom, people realized that the expectation value of energy flux at specific angles was something that could be computed in perturbation theory. And so then since then, there's been an immense amount of investigation of observables of this form. And so in the modern language, what was realized is you can compute, for example, expectation values of this average null energy or ANEC operator. And then kind of 2 years later, people kind of generalize this to multi-point correlation functions, which is where it starts to get interesting because you're actually looking at higher point correlation functions, or from the kind of CFT perspective, these are like 4-point functions in your theory. And these were realized that these are kind of a useful way of characterizing final states in collider experiments, so in particular at that time in E plus E minus collisions. And so then this kind of went dormant for quite a while, and this was kind of brought back in this paper by Hoffman and Maldacena, where they kind of really, or first of all, they brought kind of new computational tools and new ways of thinking about this, but also kind of emphasized that these are interesting observables, not just in QCD, and for QCD kind of specialists, but also just more generally in generic field theories, and in particular in conformal field theories. And so this kind of resurrected the interest in these observables, and there's been a tremendous amount of progress, in particular in conformal field theories. And so what the goal of this talk and this kind of work is to kind of recouple this with real-world QCD and to study these in colliders. So for example, these had not been kind of remeasured at the LHC, and they've been kind of abandoned. And so there's kind of a mismatch in theory and QCD studies. And so what I want to show in this talk is some kind of measurements and theory developments that have come out in the last year, which really start to kind of bridge, at least in my opinion, in an interesting way, what is possible in experiments and what is kind of interesting to theorists. And so I'll kind of go through these different examples, so it doesn't have to, I will not fully explain it now, but the kind of different things that one can do with these is first, you can go to extremely high energies now with the LHC, so where you're in a very, very perturbative regime. And so I'll show that you can really kind of measure essentially anomalous dimensions of these light ray operators very precisely, and so you can really kind of extract the spectrum of these light ray operators which appear in certain OPE limits. At slightly lower energies, you can also measure certain 2-point functions, and you can see, for example, very nicely the confinement transition. As you can kind of really image this, and so as you can see, there's kind of a gap in the calculations, so you can't calculate it, but it gives you kind of very precise measurements which show kind of really interesting aspects of the dynamics of QCD. And then very recently, people have also been able to measure these in heavy ion collisions, so in interesting QGP states, and so you can actually detect the modification due to having this kind of finite temperature state, and this kind of characterizes certain aspects of this, and by having this, these kind of new techniques that have been developed will hopefully lead to kind of improved ability to understand the quark gluon plasma. Okay, so the first thing I want to just discuss is the scaling behavior of these observables in the perturbative regime, where you kind of really understand things, and this is just an illustration that we can, or of the kind of power of these very nice high-energy colliders. So one of the things that was originally highlighted in this paper of Hoffman and Malacina is a very nice way of thinking about these operators, namely that they also admit an operator product expansion, which is sometimes called the light ray OPE. And so I'm not going to go into any of the details of this, particularly because it requires a bit of generalization for QCD, but the kind of way of thinking about it is you can essentially expand products of these light ray operators over some set of more general light ray operators, and then what it predicts, just like the local OPE, is the scaling as a function of the angle between the two detectors. And so this makes a very nice prediction for scaling behaviors and the correlations of energy flux. And so in particular, because this is related to the small energy limit, this is something which can be done very nicely inside extremely high energy jets at the LHC. And so it had not been actually studied at the LHC, but there they have an immense sample of jets, and so this is something that's kind of like perfect for experimentalists to study at the LHC. And so if you go out and do this, and so I'll show this, the data will get increasingly good throughout the talk, but so this is now being measured all the way from kind of 15 GeV jets all the way up to essentially 2 TeV jets. So this is in a really extreme regime that could not be studied before. And this is just a plot, and I'll show the more left-hand side of this with the confinement transition in a minute. But this is just a plot of this scaling of a 2-point function of these two energy flow operators. And you can see that it has this very nice power law structure, which is essentially just set by the fact that you have, or the kind of leading operators in QCD are twist 2 operators. And so you get essentially this, which is what is dominating is this kind of classical power law set by the classical twist of the operators. And so one thing you can ask is, can you, this is kind of nice, but can you go beyond and actually extract the kind of spectrum of anomalous, the anomalous exponents of these operators which appear in the OPE? And so it turns out you can do this. And so another nice organizing principle of this light ray operator product expansion is it tells you the scaling behavior of generic J-point correlation functions. And so in particular, all it says is that a kind of J minus 1 point correlator scales with the twist 2 spin J light ray operator. And so this can just be worked out in a relatively simple way. And so what it means is that if you take ratios of the scaling of an n-point correlator to a 2-point correlator, you predict that it scales with the angle to the difference of the two anomalous dimensions. So in the classical theory, this is really just flat, but you can really just extract, if you measure these, the kind of spectrum of anomalous dimensions of these twist 2 operators. And so using the data, which is now very good, you can do this, for example, for the 3/2, 4/2, 5/2, 6/2, and people have done this up to kind of 10 or very high points. And you can see nicely this scaling behavior, and in particular that it grows as a function as the number gets higher, which is just kind of the monotonicity of the Regge trajectory for these twist 2 operators. And so you can really just by measurements of this asymptotic energy flux extract the spectrum of the twist 2 operators in a kind of very clean way. And so it's a very kind of nice map between these messy experiments and actual kind of field theory data. And so this can now actually be done. So if you focus on this particular 3-point over 2-point, this has been done very precisely by the experiments now. So they've measured this scaling here over a wide range of energies, and so in particular up to extremely high energies. And so this can be computed because these anomalous dimensions, or once you've kind of simplified it with this OPE, you just need to know these anomalous dimensions. And these are known to very high loop orders in QCD. And so in particular, this is a comparison of using kind of the 3-loop anomalous dimensions with these scaling behaviors as predicted by this light ray OPE. And so it's kind of a very precision test of both this, or quantum field theory, and of this light ray OPE. And the other kind of fun thing as compared to a CFT is you'll notice that as you go up in energy, this slope gets flatter and flatter, which is just the kind of asymptotic freedom that these exponents all just kind of go to 0 in the UV. And so it kind of gives a very nice picture of understanding the energy flux in these collisions. And so just to highlight, so this is now actually one of the most, or it's the most precise measurement from jet substructure of the value of the strong coupling constant. So of course, if once you can extract the values of these exponents, and if you know how to compute them in perturbative QCD, you can then extract out the coupling. And so the kind of record extractions are at about the 1% level, and so this is already in this just kind of test attempt is getting you at the level of 4% because you have very good theory control. And so it can certainly be improved using higher order perturbative ingredients, and we're kind of pushing towards doing this to try and actually make this competitive with kind of world record extractions. Okay, so the next thing you can do, which I think is quite neat, perhaps slightly more relevant to this conference, is I can show you the kind of left side of this plot where it gives you a very nice understanding, or a very nice kind of experimental measurement, at least, of the confinement transition. And so the kind of obvious reason that one wants to do this is, so from lattice QCD, one now has very nice predictions, for example, for the mass spectrum of particles in QCD. But what you'd actually, or what one would like to more ambitiously understand is some of the dynamics of the transition between quarks and gluons and hadrons. And so, of course, this is something which you can do in collider experiments because you produce at short distances perturbative quarks and gluons, and then you detect hadrons. And so you expect that this should manifest itself very clearly when you measure these correlation functions. And so this is a measurement where before I kind of cut off the plot in the middle and showed only the right-hand side. And so this is a measurement of this 2-point correlation function, again, as a function of this angle. And so you can see on this side, you have this regime of kind of perturbative evolution in terms of quarks and gluons, where you have these non-integer scaling dimensions, and you can compute things in perturbation theory. Then you have some extremely abrupt transition at the scale of confinement. And so if you convert this into a dimensionful scale, it's just the confinement scale. And then on the other side of this, you have essentially what are non-interacting hadrons. And so this is really just an integer scaling law, which is associated just with kind of randomly distributed hadrons coming out of your detector. And you also have trivial higher point correlations. And so it gives you at least a very nice picture or kind of way of imaging this confinement transition. And so you'll notice that the kind of calculations coming from this side break down here, and coming from this side break down. And so there's currently no known way of computing this transition, but at least gives a very nice kind of target and a very nice experimental measurement of this transition. Okay, so now one thing which has come out very recently, so in the last month or so, is the ability to start measuring these in more complicated states. And so at collider experiments, you also have the possibility not just of proton-proton collisions, but of much more, so you can kind of keep going up. You can do proton-lead, xenon-xenon, proton or lead-lead, and they get these increasingly more complicated collisions where you start to actually form quark-gluon plasma. And so trying to measure these multi-point correlation functions of light ray operators gives you the possibility to start trying to understand the behavior of these light ray operators in non-trivial states. And so as I'll show, this also leads to, or allows you to kind of probe higher twist operators in the OPE in a kind of nice way. And so I'll first give a very just kind of cartoonish picture, and then I'll go through why it actually works. But so this is a measurement of this 2-point correlation function, where in black is the proton-proton result, which I showed before, and it just has this kind of scaling behavior. And then in the blue is the measurement in a lead-lead collision, which is head-on, so it's really producing the actual quark-gluon plasma. And then down here is the ratio. And so you can see at large angles, you really get this very large enhancement. So it's actually, it may look kind of small up here, but it's kind of a factor of 2 or so enhancement from the effect of the plasma. And so one kind of intuitive way of understanding why it appears at large angles is if these detectors are very kind of small together, at least in a very perturbative picture, and I'll explain this in a second later, you can kind of think of the object as kind of coming out and then splitting, but as you move these apart, it essentially makes the intermediate parton more and more off-shell and kind of drives it back into the plasma. And so this is why it will also be related to kind of higher twist effects, whereas this is kind of really a leading twist effect, which gave this scaling before. And so this is just another kind of zoom in of these ratios, where it's done as a function of how hard these kind of two large ions hit each other. So when you really form the quark-gluon plasma, you get this very large effect, and then you kind of bring them apart, and the kind of quark-gluon plasma slowly goes away until you're just back at a flat baseline where it's like proton-proton collisions. Okay, so one of the kind of typical problems with heavy ion phenomenology is that these theory calculations are based on kind of a variety of different models, which often obscure kind of the underlying physics, and they're often just typically wrong. And so, for example, this is just the exact details of the models don't matter, but this is a comparison of the data with some predictions using different models. As you can see, they're not very good. And so one thing what I'd like to understand is kind of can this operator product expansion kind of perspective lead to a nice way of at least understanding the functional form of what you measure in these states, or at least an understanding of how to characterize it, much like you could characterize the scaling of proton-proton using the kind of twist-2 scaling. And so it turns out that this is actually very easy, and so you can do it even just at the classical level without worrying about anomalous dimensions or anything. And so these objects obey an operator product expansion, where you get the kind of leading scaling coming from the twist-2 operators, and then you get higher and higher operators. So in particular, I'll focus on the twist-4 operators, which have less, or where their scaling is less divergent in theta. And so what we can understand is that the leading modification is actually captured by the presence of the twist-4 light-rate operators appearing in the OPE. And so you can then do a kind of essentially trivial exercise if you just take the ratio of this in the quark-gluon plasma and in proton-proton, and from measurements you know that the twist-4 in pure vacuum QCD are very small, and essentially what this predicts is this kind of ratio of matrix elements which are just certain numbers. And so it says essentially that the scaling is just 1, or some property which is like the energy loss, plus theta squared times another number, which is just some matrix element which you could compute. And so in particular, it essentially fixes the full angular form of this leading correction. And so this is very nice because instead of having some very complicated simulation where something comes out, it's really just 1 plus theta squared. Yeah.
What does it justify the truncation in theta?
Oh, it's just that, so there will be higher, so good. So as you go to larger angles, you'll definitely have more and more terms.
It's about like what is the scale? Like there should be some scale that depends on the.
Yeah, so so it's essentially the size of the, so this is the leading term in like the size of the nucleus over the like PT in dimensionless. So it's similar to like in the non-perturbed regime you have expansion lambda QCD over PT, and so then this is kind of coming from the UV, and so it's the leading term associated with the presence of the kind of QGP. So obviously there are more terms, and eventually it breaks down and has some more complicated shape, but this is just the kind of first time you see the QGP will be this object. Yeah. And so it's actually known from very old work of these people here, and they had nice arguments for why these matrix elements of higher twist objects are enhanced in general in nuclear states. And this is kind of because once you have multiple integrals of fields over some kind of size of a nucleus, it essentially enhances it by the size of that particular object. But here, because of the OPE, you can kind of reduce these jet substructure observables and actually use this to understand multi-point correlation functions. And so if you use this and just fit for the value, which is just a single number of this higher twist matrix element, you can actually very nicely describe the experimental data. And so instead of having some simple or some very complicated simulation, it's really just 1 plus theta squared, and then plus you put in some anomalous dimension for the twist-2 operators. And so it'd be very interesting to understand how to compute these matrix elements of these higher twist light ray operators or relate them to, for specific properties of the QGP. And so that kind of remains to be done. And the other thing which is optimistic, so there's been a lot of recent theoretical progress in understanding the structure of these higher twist light ray operators. And so by measuring higher point correlation functions and their scaling in the QGP, the hope is that one could really extract, just like one did for the twist-2 operators, the spectrum of these higher twist light ray operators, which would be quite neat if you could actually do this experimentally and kind of actually probe some of what is being understood about these higher twist light ray operators in an experimental setup. Okay, so now I just want to highlight, so that's kind of the simplest thing, which are just these 2-point functions. And so now I want to discuss, obviously, as you go to higher point functions, things become more interesting. And again, there's been a lot of amazing experimental work which actually allows one to measure these higher point correlation functions. And so this is something which surprisingly, so of course in, for example, cosmology, people have famously computed 3-point functions and higher, but there would be very little work on higher point functions of energy flux. So essentially 0, other than Malacina's work at strong coupling. But now we have a lot of techniques in scattering amplitudes to just be able to compute these objects in perturbation theory. And so I'm not going to go through it in any detail, just for time, but you can compute these objects, particularly in this collinear limit, where all these detectors are inside kind of a single, or for the experimental perspective, all inside a single jet, or said another way that you can take a kind of limit where they all go collinear, but keeping the kind of cross ratios between them generic. And so then these become interesting kind of functions of the cross ratios, much like scattering amplitudes, and one can just try and so both measure them, but also explore just their perturbative structure in quantum field theory. And so we computed the 3 and 4 point functions of these in QCD and then the 4.1 in n equals 4. And so just to give a kind of flavor, again, the details don't exactly matter, but this is the kind of tree level 3-point correlation function in n equals 4 superunions. And so you can see that just like a kind of scattering amplitude, you get very many of the similar functions. You get certain single valued polylogarithms, and they're kind of, again, very compact and have a nice analytic structure. And so this is very nice from just a purely theoretical perspective, and so it's also, people have been pushing this pretty far, so the integrand is now known up to 11 points from amplitude-hedron techniques, but it's very hard to integrate it. But for 3 and 4, we have the integrated result in terms of polylogarithms. But the kind of nice thing is that as compared to, for example, scattering amplitudes, where you then need to kind of feed them into some machine to actually make a cross-section that you can measure at a collider, here you literally just plot this function, and that's what you measure experimentally. And so just as 2 examples, and again, these become harder to visualize, and there are certain coordinates which the experimentalists like to use, but this is a measurement of a 3-point function, or more precisely, its ratio to certain 2-point functions. And so this is measured, I've drawn certain representative triangles, so kind of an equilateral triangle is up here, this squeezed triangle or flattened triangle is over here, and these squeezed triangles are down here. And this is compared with just this calculation from perturbative QCD. And so you can see that you can really start to measure these kind of interesting higher point functions, and they agree well in perturbation theory or with perturbative calculations, as they should, because these are extremely high energies. And so just to highlight that the experimentalists can do kind of even better, so these become increasingly hard to visualize, but this is a plot of a certain projection of the 4-point function. So they can really do these things to very high points. And so what's being done here is they fixed these 2 operators here, and then you spin these, and it's plotted as a function of their radius and the angle. So it's a bit, there's many variables, and so but just the impressive thing is they're able to very precisely measure kind of the energy flux within jets at a kind of very unprecedented precision. And so why would you want to do this? So they're kind of fun to play with their analytic structure in quantum field theory, but they also become even more exciting if you can start to measure them, for example, in the quark-gluon plasma. And so what I showed earlier was just this measurement of the 2-point function, where you saw some kind of enhancement at large angles. But then what one would like to do is to start measuring higher point functions in the region where you have the enhancement. And so this is something they're currently doing, and so what's shown here will be just a kind of using one of these simulations, so it shouldn't really be trusted, but it's something that they are now kind of actively doing, and so it will be out in the kind of near future from the experiments. And so what's shown over here will be the ratio of the 3-point function in the quark-gluon plasma to the vacuum at different overall sizes, and I'll kind of move out here. So when you're still in this regime, you see no difference between the 2, and then what will happen is as you kind of go into or push the operators into the QGP, you'll see a kind of change in the shape. And so as you move out like this, you can see you really get this kind of enhancement in this equilateral region. And so this was done in this particular model of Krishna and collaborators, which is this kind of hybrid where it uses a kind of a perturbative structure to source an n equals 4 plasma. And so this is really the kind of image of this wake of the QGP, which kind of fills up this equilateral region as opposed to the kind of more collinear or these kind of OPE regions, which is what you get in a weakly coupled perturbative theory. And so again, just one more comment on this. So these are, again, extremely difficult to compute from first principles. And so again, the nice thing is that these objects emit a kind of what is referred to as a celestial block decomposition. So essentially you just decompose them into certain blocks. And so again, these are just plots of the kind of shape in this space of these different blocks. And so the hope is that you can identify kind of modifications of the QGP as coming from particular blocks. And so particularly this higher twist block, again, looks very similar to this structure. And so we'd like to actually be able to kind of map out the physics and how and this kind of organizing language from this OPE is extremely nice. And so I'll conclude quickly, but I just want to show another thing of going back to the past. And so all these measurements in proton or at the LHC kind of motivated people to go back. So I did this with some people at MIT, these are the experimentalists who really actually know what they're doing, and I just kind of told them what to measure. And so there's actually all the old Aleph data, which is a very nice, clean E plus E minus collider, is on some little hard drive. And so you can actually get it and reanalyze it using kind of very modern techniques. And so we've gone back and actually measured very precisely the 2-point function over the full angular region using this old, very nice data. And so just to emphasize again, so the very nice thing about if you do this so in E plus E minus, it's like a local operator, and so you can really measure the two-point function over the full angular regime instead of just doing inside these jets like at the LHC. And the other hope is that this is something that could be amenable in QCD to some form of bootstrap technique. So this is kind of the simple, or ideally, and one would like to, or this is the kind of simplest object of this form, and so one would like to measure it very nicely. And so to see all these interesting kind of scalings and confinement transitions that I emphasized in the talk, this really requires extremely good angular resolution, which was not there in the original measurements. And so now they have very fancy unfolding techniques and all this stuff. And so what we did is kind of went back to this old data and measured this full two-point correlation function. And so this is the measurement of this two-point correlation function. So it's plotted now in the actual kind of cross ratio, which is this z, which is 1 minus cos theta over 2. So it's now plotted over the full angular regime. And so this is a confusing plot because it's logarithmic on both sides, but this side is logarithmic in 1 minus z, and this side is logarithmic in z. And so this is to really emphasize the kind of two regions. And so this really kind of shows the nice feature of this observable, that you're really kind of probing all the way from the kind of UV, which is right in the center, where there's no additional scale, so you're just probing the physics of the scale kind of Q of the operator that's injected. And then as you go to either side, you start probing physics of the scale either QZ or Q1 minus Z. So in one side, there's a scaling where you, it's kind of determined by the Wilson loop OPE, or kind of the cusp and almost dimension. So this is kind of a Sudakov regime. And then you transition again to this flat or free hadron gas case. Whereas on this side, you have this kind of library OPE, which I discussed, and then you again transition. And so in a strongly coupled theory, it would just be this dead flat scaling like this. And so you kind of very nicely see kind of all the features of QCD in this very incredibly high resolution measurement. And so then in this gray is kind of the theory calculation using the current state-of-the-art techniques. But again, this would be a very nice target for some form of kind of bootstrap techniques or something to really, it's kind of the simplest event shape observable to really do this nicely. And there's now extremely good data. So just to conclude, so hopefully I convinced you there's been a lot of progress, particularly in the connection between experiment and theory and what's being able, or what's can now be measured at the LHC in the different colliders. So one can measure very nicely the scaling and shape dependence of higher point correlation functions. And so then you can start sticking them into different states. And so the hope is that one can really use this to learn non-trivial aspects of QCD or other kind of interesting phases such as the QGP. And so thank you. And sorry if I wanted to...
Yes, so can you look at other types of correlators, like say pointing vector, correlators, pointing vectors?
Good. So there's a bunch of other, so the ones people thought more about often involve like charges. So here I focus on energy because it's it's the simplest thing in one computer purely in perturbation theory. So using kind of, or if you add certain non-perturbative information, then you can start to do it with charges. And so you can do it, for example, like plus minus, or energy flux on plus, energy flux on minus. And this probes more aspects of the hadronization transition. You can see, for example, that like plus minus are kind of, or if you believe some string breaking picture, they should be correlated. You can actually get that out of calculations. And so part of it is driven by what can be experimentally measured, and that's essentially like energy and charge. And so people thought a little bit like about angular momentum and other things, but those are less explored a little bit just because they're less, or I don't know exactly how an experimentalist can measure it. So part of it is just driven by what can be measured experimentally.
No.
So when you talked about the higher point functions, you mentioned the calculation in n equal to 4 super Young mills. Have this been computed also in QCD, or?
Good. So yes. So you mean like the perturbative structure? Yeah. So is that the one you're?
The question is whether this has been done in QCD.
Yeah. So for the 3-point function, we've done it in QCD, and so I just showed this one because it's a bit shorter.
Yeah.
But in QCD, it's the exact same functions. You just get very long polynomials in front of them. And so what happens, or more precisely, is in QCD, these have poles in like 1 over z minus z bar. And so in QCD, you get much more singular and 1 over, so you don't actually have it's very similar to the cosmological correlator case where you don't have a singularity there, that it cancels. But in QCD, you get like a fictitious pole that's like z minus z bar to the 24 or something. And so you get these crazy polynomials that all cancel. And so that's what makes it difficult. So the 4.1, we've so far only done it in n equals 4. It's certainly possible in QCD. It's just the like integral reduction is a bit hard. So we know the functions that will appear, and it's something that like it will be done in the next years. It's just like kind of a bottleneck from a purely computational perspective. But one understands the functions, and then beyond that, the like integrands are not even known beyond that in QCD. So part of the thing from n equals 4 is you can get the integrands very efficiently, and the integrands are quite compact. Yeah.
Is the n equal 4 the planar limit, or are you assuming n equal SU of 3?
Yeah, so this is just planar n equals 4. Yeah, yeah, and this is also planar n equals 4. Yeah, yeah.
So when you say you have the QCD one, it's planar?
No, it's non. So the QCD one is just the full. It's just the full QCD.
thing, okay.
And at this level, so that's like because one is really just doing things in perturbation theory. All like loosely, what it does is it just simplifies the integrand. So if you can do it in n equals 4, you can power it through in QCD. It will be the same functions, just a whole lot of rational prefactors.
Right? Yeah, one more question?
Back to plot very well the confinement and the asymptotic freedom data when you get this transition. So do you expect the divergence in the transition or?
So you get it, if you take the perturbative result, it just kind of blows up. And so you're just losing control. And so that's also true, or that's in a CFT that's physical, that it really should just diverge. But here, you need something, yeah, so here in perturbation theory it diverges, and so you can do kind of a like conformal perturbation theory, or from both sides you can compute like a series of corrections. And what they actually do is make it more and more steep. So like this in perturbation theory in these units, this goes like 1 over theta, then you get to turn this like lambda QCD over theta squared, and then lambda squared over like higher and higher powers, and so they just kind of blow up worse and worse. And so you need some way of resumming them, or something like there's no known way to make it turn over. So one thing you can do is you can like Higgs the theory, and then you can just compute it with like a finite mass. And so then you get a nice curve that turns over, and it has some actually like, there's a kind of non-analyticity of the mass, like out of the complex plane. And so like the series just doesn't converge from either side. But in the actual QCD case, yeah, I don't know.
And in the confining case, you plot the data and the line is.
So this line, which is here, is really just, it's a geometric scaling of like just a gas of hadrons. You can just compute in a gas of hadrons. And so it's really like in this unit, it's like theta. It's literally, it's just because it's logarithmic, it's really just literally theta. But then you can compute using, you can then compute corrections of those where you incorporate interactions between the hadrons. But again, it's not known how to make it turn. So it's kind of both sides, the expansion just gets worse and worse and worse. But it'd be nice to know how to do it from some form of lattice observable or something that could actually characterize the transition.
One last question?
Yes, sorry to keep people from the drinks, but I mean, could you think about this turnover also in terms of conformal anomaly? So you're just talking about conformal correlators, but you of course have conformal anomaly coming in, and that could explain this deviation.
Yeah, so I think okay. I don't know off the top what a conformal anomaly, like if you really just mean like a beta function, or
Yeah, that's a one.
yeah, so like on this side, so already like
Yeah.
we're also lying a little bit when I gave the formulas, because one is of course computing these in actual full QCD to compute the scaling. So it doesn't have these exact power laws, but it's already incorporating all the data function terms. And so again, the problem is you don't know how to resum them. So at any fixed order of these, you can compute but this is just at the level you have control over, this is just a kind of logarithmic correction, and you really need something that changes the power law from this to this. And so that you just kind of by definition don't have control over perturbatively. Yeah.
Okay, let's thank Ian again.